right. Can everyone hear me, hopefully? I can hear me. It's actually really weird having your own voice come from behind you. I don't know if you've ever experienced this. So, I'm Steve. I'm very easy to find on the internet, if you are so inclined. I work for ThoughtWorks. We are a global technology consultancy. We actually have an office just like a 10-minute walk from here, which I'm going to be going to right after this. So if you ever want to work with some really lovely, clever people, come say hi. Now, the title of this talk is Building a Culture from Chaos. I'll get to the building a culture part in a sec, but the chaos part refers to chaos engineering. We're going to be talking about chaos engineering today. There's a lot of you in the room. So show of hands, please. Who here has ever done chaos engineering? Put your hands up. I see one hand. There's some lights in my eyes. Maybe I'm missing others, but there's not a majority of people putting their hands up. So I've asked this question a lot in a lot of different, fairly technical rooms, and I've never seen everyone put their hands up. It's something that is, I think, relatively well known, but very far from mainstream. So I think it's worth kind of kicking off with a little bit of an introduction to what is chaos engineering. And I could explain this in a couple of different ways, and I will kind of give you a couple of different perspectives on what chaos engineering is. But I'm going to start with a story of sort of how chaos engineering was invented, how it came to be. And this story, like most stories in our industry, starts about 2010 at Netflix. And pause for laughter. So around this time, Netflix was moving to the cloud. So they were moving from their own data centers to the public cloud, AWS specifically. And as they were doing this, they decided to do more than just a lift and shift, right? They weren't just copy-pasting all of their systems from a data center to public cloud. They took this as an opportunity to re-architect their systems. They took the large services, the big monolithic services that ran their business, and they started breaking them down into smaller, independently deployable services. They were doing what we today would call a microservices transformation. Maybe I'm sure many people in this room have been part of a microservices transformation. And as they were doing this, they realized that if they did things badly, they would make things a lot worse. See, we often kind of think about microservices. We often associate microservices with scalability and resilience to failure, but you don't get that stuff automatically. You don't get that stuff for free. You see, if Netflix took one service that ran their entire business, and they broke it into 100 or 1,000 services that ran their entire business, and if any one of those services failing could bring down their entire business, they've gone from having one point of failure to thousands of single points of failure, which is not great. So in order to avoid this, Netflix put together the Netflix engineering principles. Now, full disclosure, I have never worked for Netflix, but I do know people who have, and they've told me that these were printed out on the wall. So all the engineers were reminded of this every single day. And the first of the Netflix engineering principles was that you should never, ever build a single point of failure. So no service going down should bring down your entire business. No single point of failure. It's a simple idea, but it's an incredibly important one. In fact, it's so important that the second Netflix engineering principle was to never, ever trust that you got the first one right. And this is a great thing to kind of print out on a wall. Always gets a laugh, but they actually built a tool to do this. They built a tool to never trust that they built a system without a single point of failure. And if you've heard of chaos engineering, you've probably heard of Chaos Monkey. So what Chaos Monkey does when it's turned on, when it's activated, is it looks at the Netflix production infrastructure, and it starts randomly turning off servers. Sort of pulls the cable, pulls the power plug out of them to simulate a real failure. They don't do this 24/7. They only do this kind of on the week, on weekdays when Netflix engineers are in the office, so they can respond if something does go badly wrong. But what they're doing here is they are testing their hypothesis, right? So they have this hypothesis that they have built a system without single points of failure. And if they're right, Chaos Monkey shouldn't really bring down the business. It might cause a little bit of service degradation if they take down the recommendations service. Maybe you don't get your recommendations, but the business as a whole should keep running. So they ran Chaos Monkey over and over and over again, constantly testing for these single points of failure. And they had a huge amount of success with this. In fact, they actually went on to build more kind of monkey-themed tools. So Chaos Monkey's big brothers, Chaos Gorilla and Chaos Kong, they kind of do the same thing, but a slightly bigger scale, so simulating the failure of entire data centers and availability zones. Very fun. They don't do this every single day. They do these a little bit more infrequently because they're slightly bigger failures. But really what they're testing here is if a meteorite wiped out the west coast of the US, people should still be able to watch Orange is the New Black. It's critical infrastructure, okay? Don't lie. This is important. And they had other monkey-themed tools as well. One of my personal favorites is Latency Monkey. What Latency Monkey does is it simulates latency. It takes network requests, and it makes them a bit slower. That's all, right? So a request that used to take 200 milliseconds, well, now it takes 2 seconds, or 20 seconds, or a minute. And that's exactly the kind of failure that we see in the real world, right? People trip over Cat5 cables. Network switches overheat. Sometimes things just get a bit slow for a few minutes, right? And again, what they're doing here is they're validating that they haven't built a single point of failure. They're validating that they haven't accidentally set their timeouts wrong or their retry logic wrong in such a way that latency would bring down their system. And they kind of went on and built a whole suite of monkey-themed tools. They called them the Simian Army. Just for a little bit of context, this is from a previous version of the internet, where internet-based monkeys were good and cool and not just scams. But got to go for NFTs today, haven't I? Thank you, thank you. And Netflix kind of going out and talking about this, they published these tools. You can download and run these tomorrow if you want. Netflix talking about these tools, publishing these tools, I think really led to chaos engineering gaining traction, people becoming interested in this approach. And looking back on it, Netflix kind of realized that they invented something. And they actually went ahead and bought principlesofchaos.org. You can go here today if you so choose, where they actually kind of described this craft, this technique that they had invented, chaos engineering. And they said, chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. I quite like this description because there's a couple of good points here. So first of all, they point out it's a discipline, right? Very often when we're talking about chaos engineering, we frame it as we're just releasing the monkeys and just randomly turning off servers. But there is a discipline to this. I mean, I was guilty. I just did that a few minutes ago, right? But there is a real discipline to this, and we're going to be talking about what that discipline involves in just a little bit. I also like, again, that it calls out it's an experimental approach. Netflix has a hypothesis that they have built a system with no single points of failure. They are testing that hypothesis. We sometimes call these runs of Chaos Monkey chaos experiments, or chaos variables that we're introducing into the system. And I also like that it calls out that it's about helping the system withstand the turbulent conditions in production. Because these failures, servers going down, are things that really happen. Even if you're working in with a public cloud, you press a button, you run a Terraform script, and you get a server. It just appears out of nowhere. There's still hardware under there. There's still a server that you are running your software on, and hardware fails sometimes. I like chaos engineering because I sometimes describe it as an honest approach to engineering. It doesn't try to pretend that everything is perfect. We're running on these platonic ideals of machines. No, we're running on real hardware, and real hardware breaks sometimes. So I sometimes sort of frame chaos engineering as the sort of core loop here. We've got our chaos experiments, right? This is when we unleash the monkeys. This is where we try and break things. Then once we induce some failures, once failures occur, we try to learn from those failures. We try to figure out what went wrong. There's lots of great writing on this. I will have a big page of references at the end, so you don't need to worry about taking too many pictures right now. But writers like Sidney Dekker, Todd Conklin, John Allspore have done some really, really fantastic work looking at how we can learn from failures, how we can understand what's going on in our systems. And once we've learned, once we've understood something from that failure, we use that learning to improve the resilience of the system. This word resilience here is key, right? So distinct from robustness. Robustness means that we prevent the failure happening. Resilience means we are able to adapt to that failure. If we caused a failure, we want to make sure that failure can't happen again in the future. So we're improving the system's resilience. Some people would call this, fixing bugs. I don't necessarily agree with that, but that's more of a philosophical thing. But at its core, this is the core loop of chaos engineering. We induce failures, we learn from the failures, and then we improve the system's resilience. So now that you're all chaos engineering experts, I have a little bit of an admission, which is that this talk, while it is ostensibly about chaos engineering, I actually really want to talk about complex systems today. So, another question. Who here would say that you work in a complex system? Show of hands, please. Okay, I'm going to say that's the majority of people putting their hands up there. Okay, now what's interesting about that is I haven't defined what a complex system is yet. But you all put your hands up very quickly, which is bold. I like that. But this term actually has meaning, okay? So the study of complex adaptive systems is an entire field of research. And there's a couple of ways we can think about this. One way of thinking about complex systems is to look at their properties. Look at how do they look? One thing that we would generally see with complex systems is a high degree of multiplicity. What we mean by that is there's lots of stuff in them. There's lots of elements, lots of moving parts, right? If you've heard this phrase, lots of moving parts, that might be a sign. Maybe you're looking at a complex system. But that probably isn't enough, right? If you're walking on the beach, you've got sand, right? There's lots of grains of sand, but is that really what we mean when we say complex system? Maybe not. That's an example from Paul Cilliers there. So we also need a high degree of interdependence. We need lots of connections between these things. So these elements, these nodes in these complex systems communicate. They send information and energy between each other. These connections can be non-linear. So a very small input can lead to a very large output. For example, if one of you right now starts a rumor that there's some really, really good swag at one of the tables outside, that might lead to a huge crowd of people gathering there. So Small input, large output. That's a non-linear interaction. Because you're passing information between the elements of the people in this crowd, which is probably a complex system. And we also have a high degree of diversity. So it's not just these grains of sand. The people in this crowd are not all the same. There's a high degree of diversity in the nodes in a complex system, which also means, of course, that there's a high degree of diversity in those connections between them. The relationship you have with your colleagues or the people in this room is probably different to the relationship you have with your family. It's not that one's better or one's worse, maybe, but they are different types of interactions. And when we're talking about complex systems, it's these interactions, these connections between the elements that are key. And this is a start, but this isn't really enough. I think a better way of understanding complex systems is to think about their behavior. How do they act? Not just how do they look, but how do they act? One very interesting thing about complex systems is that observers... Oh, sorry, I missed a slide. Tell me, does this look familiar to anyone? Does this? See, I think when I ask this question, who here works with a complex system, we're all used to looking at diagrams like this, right? Who's seen an architecture diagram like this? We understand that something here is difficult. We might call it complex. We understand that something about this is somewhat complex. And I think this is why a lot of people, particularly in the tech industry, always say, yes, we work with complex systems. Now, this is great, thinking again about these properties of complex systems, but I think it's, as I said, I think it's more useful to think about the behavior of complex systems. And one of the behaviors of complex systems is that observers change the system. Anyone who gets stage fright will understand this, right? There's a very big difference between talking to your bathroom mirror and a crowd full of people. Luckily, I don't get stage fright, but I do. I was pairing with someone last week, and I misspelled my own name 6 times in a row. Because observers change the system. They become a part of the system. And just that observation changes things. This has very interesting implications for people like myself who are consultants. It's impossible to be this perfect fly on the wall, just hovering and watching from a distance, completely neutral, because you become a part of the system. And because observers change the system, every time they observe, every time they interact with the system adapts. The system changes. And this is probably not news to anyone, right? Systems change. Systems evolve and adapt and change over time. Sure. But this has really, really important implications for how we work with these systems. Because a plan that worked yesterday might not work today. Who here remembers March 2020? Everyone remembers that month, yeah. So I spent most of March 2020 in Berlin, where I live, and that was pretty tough, right? We had pretty strict lockdown, basically the strictest lockdown we had ever experienced. Businesses were shut. Things that we used to think of as completely normal were impossible overnight. And that was really, really difficult. But there was also a sense that we were kind of in this together. Not quite true for the British Conservative Party, but there was a sense that as difficult and as challenging and as new as it is, or as it was, we were in this together and we were able to kind of like pull through and ultimately make it out the other side. Now let me ask you a question. If the government tomorrow implemented the exact same lockdown measures that they implemented in March 2020, would that have the same effect? Probably not. A plan that worked yesterday might not work today, Because every time we interact with the system changes, the system adapts. And this has incredibly important implications for how we need to work with these complex systems. We need to co-evolve with the system. If we don't, we're going to get left behind. And because we have all of these elements, because we have all of these parts of the system communicating with each other, the system is constantly adapting to the world around it and your interactions with it, we have unintended consequences. We sometimes frame unintended consequences as rare, wild occurrences, but in complex systems, they are a certainty. As Barry Commoner puts it, the first law of ecology is that you never just change one thing. If the image in the background looks familiar to you, it's because it's one of the most widely distributed images in human history. It's known as the blue marble, and it was taken by the crew of Apollo 17 on their way to the moon. Now, most of the crew time in the Apollo program was very carefully timed, carefully structured so they took the exact right measurements at the exact right time. But this particular picture was just taken when the crew had a few spare moments. If one of them floated over to the window and snapped this picture of the Earth receding in the distance. And a few years later, after the Apollo program wrapped up, there was a campaign to release these images to the public domain. They were released, of course, and for the first time in human history, the whole Earth was able to see the whole Earth. The whole Earth was able to look down on our planet and not see people and countries and borders, but they saw a fragile oasis hanging in the darkness of space. This image has been credited with shaping the environmental movement as it stands today. We could very reasonably call the environmental movement as we understand it today an unintended consequence of those astronauts taking this picture. But if we went back in time and took this picture again, could we guarantee the same environmental movement? If we went back in time, could we have predicted the environmental movement given this picture? Unintended consequences are the norm in complex systems. The system is constantly adapting around us. It's changing and evolving, and we need to co-evolve with it. As the Greek philosopher Heraclitus put it, you can't step in the same river twice. The system is changing around us, and we need to take that into account. And there's lots more things that we can talk about with respect to complex systems. Lots more properties and behaviors that they have, and I don't have time to get into all of them today. But one thing becomes incredibly clear when we start thinking about complex systems. And that is that we need new approaches if we're going to be working with complex systems. A technique, an approach that is designed for an ordered, deterministic, predictable system is not going to work with a complex adaptive system. And when I look at the, for lack of a better term, the agile community, I see a lot of techniques that make sense for complex systems. Who here has heard of big modeling up front, or big design up front, or big requirements up front, right? It's got a couple of different names. This is the idea that before you start building something, you need to put as much time and effort as possible into the design and the modeling. Measure twice, cut once, right? You do as much planning before you actually start building. And this is talked about a lot in the Agile community, in particular the extreme programming community, of which I'm a big fan. And it's usually framed as an anti-pattern. And this shows an awareness of complex systems. Because no matter how good our plan is, there will always be unintended consequences. No matter how good our plan is, the system is going to evolve along with us, and we need to adapt our plan as we go. We cannot, no matter how hard we try, we cannot model our way to an answer in a system that is constantly evolving around us. So this is an approach, looking at this as an anti-pattern is an approach that is coherent and cogent with a complex systems approach. Even the Agile Manifesto, one of my favorite manifestos, has this line about responding to change over following a plan. Again, there is value in the things on the right. We just think there's more value in the things on the left. Yes, you should probably have a plan. Yes, you should probably follow a plan to a degree, but you need to be ready to respond to change, because no matter how good your plan is, the system is going to evolve around you. Again, this shows an awareness of complex systems. A lot of these agile ideas, agile concepts, don't explicitly reference complex adaptive systems. Some do. I like this book, Edge, Value-Driven Digital Transformation. Full disclosure, this is written by 3 of my colleagues at ThoughtWorks. I'm not getting paid anything extra to recommend this book. I do genuinely think it's a good book. And it's a book that very explicitly takes its title from the edge of chaos, from complex adaptive systems theory. And this whole book is about how to run a business, how to operate a business in a complex environment. They say things like, in times of uncertainty in complex systems, our traditional reliance on planning won't work. It's not that we don't plan, we do, we just don't believe our plans will survive reality. We need new approaches when we are dealing with the uncertainty and the non-determinism of complex adaptive systems. And while I like this book, I will recommend this book to most people, I don't think you need to read a whole book to get these insights. This is a really simple idea. We accept failure that is coherent with complex systems. Failure is going to happen. You might as well take it as an opportunity to learn. You might have read the State of DevOps report or the Accelerate book, which calls out the Western culture model, pointing out that high-performing organizations see failure as an opportunity to learn, not just as an opportunity to punish people. This is such a common idea. I've actually physically seen this framed and put on walls in multiple offices from multiple different companies. I don't know if anyone else has seen this. A little while ago, I was talking with Dave Snowden, who's a researcher in complex adaptive systems, and he said that whenever you see this sign, we accept failure, what you're actually observing is a process of Darwinian selection to root out the fatally naive. Look, we put up a sign saying, admit when you make a mistake. Let's see who's dumb enough to actually do it. I don't completely agree with him. It is entirely possible to do this, to actually genuinely accept and embrace failure, but it's also possible to not do that. It's also possible to put this sign up and not actually change. We say we accept failure, but anytime anything goes wrong, we punish and we shame and we fire. It's entirely possible to screw this up. And I was talking with a client a couple of months ago about some changes that we wanted to make to their organization, to their team. And they, at the end of the conversation, they said, "That's great, Steve. Completely agree with everything you just said. This all sounds like an amazing plan. But how do we make that part of our culture? How do we make it so that this is not just a thing we put on the wall, a sign we hang up? How do we make this something that we actually do? How do we make this part of our culture?" I really liked this question. I thought this was a really astute question, right? Because it acknowledges that it's so easy to trick ourselves into thinking we're changing our culture when we're really just printing things out and sticking them on a poster. But how do we change culture is unfortunately a complex problem, and it's not an easy thing to solve. But there is a perspective I like from this guy. This is Aristotle, by the way. And in Nicomachean Ethics, he was talking about what it means to be good, how you become and act as a good person. And he said, "We are what we repeatedly do. Excellence, then, is not an act, but a habit." Full disclosure, that was not actually Aristotle. That was a later philosopher who was paraphrasing Aristotle. Just, it's important to cite your sources. Okay, so, but I like the idea, right? We are what we repeatedly do. Excellence is not, our culture is not what we say it is. It's not what we hang on the wall and put on a poster. Excellence, our culture, is what we repeatedly do. And I like this because this changes our problem. Okay? We're not asking, how do we make accepting failure a part of our culture? That's a messy, difficult problem. Now we have a different question. How do we make accepting failure a habit? Well, it's there, it's step 2. Right? This is the whole point of chaos engineering, is that you make learning from failure a habit. You make it something that you do every single day. Another good idea, right, that you can buy a poster and stick on your wall is that no plan survives first contact with the enemy. Very difficult to source the quote for this one, like the original person. I personally prefer Mike Tyson's formulation of this quote, which is that everyone has a plan until they get punched in the mouth. Right, but again, things will go wrong. Your plan will need to change no matter how good your plan is. This is a good idea. This is something that is coherent with a complex systems approach. Now, you could buy this off Etsy. It costs about €20, and I think like €6 postage and packing. You do you. I don't think that this is going to change your culture, though. The question is, how do we make understanding this a habit? How do we make this part of our culture? Again, it's step 2. It's right there. Yes, this was something which Netflix, printed out on their walls and said, these are our engineering principles, but they built a tool to make it real. They built a tool to do this every day, to make it not just an act, but a habit. So, looking at this, core loop of chaos engineering, we see a lot of stuff about these chaos experiments, right? There's thousands and thousands of articles on how to get started with Chaos Monkey, because that's a very good title for an article. And there's a lot of discipline, there's a lot of skills that go into designing a chaos experiment. One of the things that you need to do is think very carefully about what you're actually attacking. Again, we often kind of frame chaos engineering as just, we just release the monkeys and they start killing random servers. But no, there is a discipline to this. You need to be thinking about how you maximize your learning. As my friend Russ Miles puts it, if you take a service that you know is a single point of failure, and then you run a chaos experiment against it, and it causes your entire system to go down, you haven't actually learned anything. You've just annoyed someone. So we need to think carefully about what we're actually targeting here, about how we actually maximize our learning. And we also need to think carefully about how we limit the blast radius of our experiments. Things will go wrong, so how do we stop it bringing down our entire business? And we can do this in lots of different ways. We can target just a subset of our services. Maybe we start with the less critical services. Or maybe we start on our testing or our staging environment. We need to think about how we, don't bring down the entire business. If you bring down your entire business, you will learn a lot, but it might be your last chaos experiment. So we do need to think about how we limit our blast radius. We also need to make sure we have monitoring in place. We need to make sure we can actually see what's going on in our systems. Understand, hey, if I bring down this system, what happens? And then the deeper topic there of observability, so I can really, really get into the weeds and understand why and exactly what's going on inside. Again, if you don't have monitoring in place, you're just pressing a button and walking away. That's not a very good experiment. You're not going to learn a lot from that. And we also need to think about rollbacks. Now, we have a huge advantage as software engineers, which is that we can usually do this in code. We can usually automate this. I worked on a team once that we had a fully automated setup for our entire production cluster. We could bring up our entire production cluster in a couple of minutes with just a few Terraform configs. Very, very powerful, a great way to recover from disasters, but also, you really don't want to be writing those Terraform files when your business is burning down. So you probably do want to have these in place before you go. So there's a lot of discipline that goes into designing chaos experiments. Now, a couple of years ago, I was reading this article from Dave Snowden, 7 Principles of Intervention in Complex Systems. And he talked about how we interact with complex systems. He points out that when we have this uncertainty, this unpredictability, this non-determinism, we need to be thinking about these as experiments. We're not sure if they're going to work, so we need to treat them as experiments. And we don't just want to run every experiment someone can think of. We actually want to ask, well, is this really a coherent idea? Remember, in a complex system, we can't model our way to the answer. But we can ask, well, does this make sense? Does this roughly fit with reality as far as we understand it? Does this seem like a reasonable bet? We also want to make sure that those experiments are safe to fail, because some of these experiments will fail. And when they fail, you want to make sure you don't bring down your entire business, your entire organization. You also want to make sure you have monitoring in place, so you can see what's going on, either in real time or at least fast enough that you are able to respond. Because if things go badly wrong, you want to have a damping strategy in place, some way of limiting the energy that we're putting into this bad thing. The flip side of this is we also need an amplification strategy. What if we try something and it goes really, really well? How do we do more of that? So if you're looking at these 2 lists, you'll notice that when we're designing chaos experiments and when we're experimenting in complex systems, in both cases, we need to think carefully about what experiments we're actually running. We don't just want to run everything we can think of. In both cases, we want to make sure we don't do too much damage. In both cases, we want to make sure we have monitoring in place. And in both cases, we need some way of undoing damage if we do too much. Now, if you're looking at this and you're thinking to yourself, well, that's the same list. Good job. You figured out the point of the talk, which is that a lot of the skills you need to work with complex systems are the same skills that we need to work in chaos engineering. I'm going to be very clear here. I don't think this is a silver bullet. I don't think that if you start doing chaos engineering, you will magically be able to surf the difficulties of complex systems. There's a lot more to learn. There's loads more techniques to learn. that are important to working with complex systems. But I think starting with chaos engineering is a pretty good first step to really internalize these ideas about uncertainty and unpredictability and learning from failure. So getting back to this, it's easy to find lots and lots of articles about chaos experiments. All right? Like I said, there's thousands of articles called How to Get Started with Chaos Monkey. Fantastic search engine optimization, right? There's lots and lots of articles about how to learn from failures. You should really dig into this. It's a fascinating and a really important topic. And there's lots of stuff about improving the resilience of the system, which is an incredibly important topic. Chaos engineering isn't just about stopping things failing, it's about helping us deal with the failures that do happen. But this is a first-order effect. We do chaos engineering to improve the resilience of our system. And this talk is about the second-order effects of chaos engineering. Not just how does it change our system, but how does it change our culture? How does it change how we think about ourselves and our work and the world around us? And for that matter, what about the other techniques we use? I'm a big test-driven development fan. We all know what the first-order effect of TDD is. You get more tests. Big fan of tests. They're great. But what are the second-order effects? How does it change how the team looks at their work? How does it change how the team understands their responsibilities? How does it change the culture? How about continuous integration, continuous delivery, pairing, continuous deployment? All of these techniques, we understand the first-order effects, but what are the second-order effects? I'm out of time. I will leave that one for you to think about over the weekend. I'll say thank you. References. There you go. There's the Edge book I mentioned. This is a really good book about complex systems. Dynamics in Action, very, very academic. I really like Complexity and Postmodernism. It's a very academic book, but it is, I think, very accessible kind of dive into complex systems. Managing Complexity and Chaos in Times of Crisis. It's a free EU field guide. You can watch that for free. And the Debriefing Facilitation Guide, the ETSI Debriefing Facilitation Guide, is a fantastic look about how to learn from failures. There you go, if you want to. Yeah, the whole point of this talk was to get you to read some of these things. So yeah, go